Today I have the pleasure to introduce our first speaker, Vindas Mele from the University of Kentucky, and he will be telling us about the decompositions of Erhart Hdr polynomials for rational polytopes. Take it ahead.
Thanks for the introduction, Jose. Hi, everybody. Good morning. So maybe I'll start off with a little bit of context or thanks. So these are the people that are behind this project with me, my collaborators. On the left is Matthias Beck, who's a professor at SF State and is currently at FU Berlin, who was one of my master's thesis advisors. And then on the right is Benjamin Braun, who is my PhD advisor at the University of Kentucky. And I think whenever you're funded by the NSF, you should say that you have had money from them to support you. So that's there too. So what are the main characters? The main characters of this story are polytopes. And maybe the middle child complex, or like the ones that are sometimes like forgotten or excluded sometimes, are the rational polytopes. And I say that because I feel like I owe my sister a lot of the sister after me a lot of apologies. But yeah, so these are the rational polytopes. And so a rational polytopes are the convex hull finitely many points in Q to the D. And so, you know, I imagine you all are have seen polytopes at some point in your life. But if you haven't, you should just, well, I'm sure you've seen them, but if you want to think about them as higher generalizations of polygons in 3 dimensions, people like to say, you know, you throw up some points up into space and then you saran wrap them, and then you get this shape with flat sides, and that is a convex polytope. And so we dropped the word convex because we assume our polytopes are always convex, yeah. But the vertices are going to have rational coordinates, okay. And so for a positive integer t, I'm going to let L sub p of t denote the number of integer lattice points in the teeth dilate. So all I'm doing is taking a positive integral dilate of my polytope, and I'm going to count the number of lattice points inside that polytope. Okay. Also, I can't see the chat, but if you have questions, Jose can ask them if you put them in the chat. And then in the 60s, in 1962, Eugen Erhart proved that this counting function, L sub p of t, is in fact a quasi polynomial of this form. Okay, actually, I'm like pointing and I don't even know if you can see my cursor. Erhart proved that this lattice point enumerator is a quasi polynomial of this form, where these k sub I are periodic functions. And so we call this the Erhart quasi polynomial, and it's a periodic function. So where we have some period where it cycles through, and we call each period divides the denominator q of p of the polytope. And so we define this denominator to be the least common multiple of all its vertex coordinate denominators. Okay. And so you might say, okay, well, Andres, what is a quasi polynomial? So again, here's the definition of a quasi polynomial, and you can read it, and then you can still be like, okay, that does not mean anything to me. And so people like to give this form a little bit. It's more user-friendly in some sense. And so it's essentially a piecewise function where each of these f sub I are polynomials themselves, and it cycles through some period. Okay. Everybody with me? Okay, awesome. Nothing too crazy. As combinatorialists, we like to encode things in generating functions. And so we call the corresponding generating function of this Erhart quasi polynomial the Erhart series. And you can prove that it has this nice rational form. If you're more familiar with the lattice case, where the denominator is 1, you would have that this q is 1, so you would disappear. It would disappear, right? And so you might see it in this form. I will say that I'm taking this nice rational form and I'm never reducing it, right? Like as long as it has this form, it's not going to necessarily be in lowest terms. Okay. And so we call the numerator of this rational function the Hdr polynomial. And so that's what I'm going to try to show is some decompositions for that. Okay. And so what is known about the Erhart theory of rational polytopes? I guess I should do an example to get you to understand this. And I kept my hand-drawn pictures just for Galen. And so this is my fourth grade rendition of a polytope. And so this is a convex hull of these 4 points, right? Notice that the vertices are rational, right? These are the corresponding vertices. And what we care about is dilating the polytope by integral dilates, and we're going to count the number of lattice points. Yeah. And in this particular case, you can see that the number of lattice points kind of depends whether we have an even dilation or an odd dilation. And that's because, oops, I don't know what I did. There it goes. The period here is 2, right? The period, the denominator or the period is 2, and the denominator of this thing is the least common multiple of all vertex coordinate denominators, which is 2. Okay. And so this is the corresponding Erhart quasi polynomial. And then we put it, here's a little bit of the work when you run it through the corresponding Erhart series. And one thing that you might notice is that this Hdr polynomial, well, as combinatorialists, we like to find some patterns. And so I normally would ask you, what nice things do you see? But because this is a short talk, I'll tell you the first thing that I see is that it's palindromic, right? It's symmetric. And so hopefully there'll be an answer to this. And if I don't give an answer to it, I always tell people, please remind me, because one of my theorems is supposed to imply why this is palindromic, but we'll get to that. Some known results about the Erhart theory of rational polytopes. So there's this reciprocity result by Ian MacDonald and in some case for Erhart from the 70s that says, if I plug in a negative dilate in a sense, some negative value into negative integer value t, I count the number of interior lattice points of my polytope up to a sign. So it's a very nice thing. And it's the kind of one of the remarkable things about combinatorics is like, why should any reciprocity theorem actually hold when you plug in negative things? But it's quite nice. And so you have the corresponding relationship with the Erhart series. And then in the 80s, Richard Stanley proved that the coefficients of the Hdr polynomial are non-negative. And so one of the results that I'll show you is a kind of a different direction towards getting this result. And then the last thing that I want to mention on this slide is Stanley's monotonicity result. And so what is this result saying? This is saying if you have a rational polytope P contained in some larger polytope Q, where I can dilate them both by some integer Q, where they go back, both are integer polytopes. This result says that the Hdr coefficients of Q dominate the corresponding coefficients of the Hdr polynomial of P. Okay. Hopefully that made sense. Okay. And so what are the goals? I'm going to show you 2 decompositions. One is a generalization of a result by Beck and Macmillan from the 80s, and another one by Stapledon in 2009. Okay. And so I'll do some setup and notation real quick. So what is a rational pointed simplicial cone? It is a set of this following form. Okay. And so I'll show you a picture. That's the formal definition, but I'll show you the picture in just a little bit. And then we also have this associated open parallelepiped to this simplicial cone. Again, I'll show you a picture of what that looks like, but you should be thinking a parallelepiped in some dimension. Okay. And then I need this projection U that is the projection onto the last coordinate, so that we can define this box polynomial, which is z to the u of v, which is just essentially keeping track of all the integer points in my open parallelepiped. Okay, so it's a polynomial that's in some sense, yeah, keeping track of that information. Okay. So here's a small example. Here is the set W, which is just 1, 3, and 2, 3, and the corresponding box. Like I said, we should just think open parallelepiped, yeah, and it has 2 lattice points inside the box, right? Because we don't care, because it's open, we don't care what's on the boundary. And here is the corresponding box polynomial. Again, it's just the box polynomial is encoding somehow these integer lattice points. We also define the half-open variant of the parallelepiped, and we call this the fundamental parallelepiped. And so it's just it's half open, so now we can include part of the boundary. Okay. And so we also care about coning over the polytope. So the idea here is that you're appending a 1 to the last coordinate of the vertices, and so you're really in 2 dimensions you get a visual like this, where it looks like a cone over the polytope, and you can retrieve the Q dilate of the polytope by slicing the cone at a certain height. Okay. And again, maybe you've seen triangulations. Triangulations we're essentially splitting the polytope into simplices. In this case, I'm keeping track of them in all dimensions. So this is a triangulation of my original rectangle P, and this has 4 2-dimensional simplices, and then you can count all the 1-dimensional simplices, which are the edges, and then it has 4. Well, I guess in this triangulation, it would have 5 0-dimensional simplices, and then we keep track of the empty set as one of these things. Okay. And so instead, I've defined the denominator of a polytope. I can also define the denominator of a triangulation, right? Which might change because, for example, this triangulation now sees this inside point. And so I'm just going to say that the denominator T is the least common multiple of all vertex coordinate denominators of the faces of this triangulation. Okay. And so, wow, time is going fast. Here is the H polynomial. The H polynomial is this. I should say this is the H polynomial of the link. And I won't say anything other than this is encoding kind of the topology of the polytope. Okay, so it's keeping track of the faces. And so we can get the H-star polynomial of a simplex by summing over, or it's the sum of this z to the u of v, where we're now counting just the number of lattice points in the fundamental parallelepiped. Okay. And so here's the decomposition a la Beck-Macmullen. So I'm going to let P be a rational polytope and T be a triangulation with denominator Q. I'm going to, for any M simplex, I'm going to associate the set W to be the integral ray generators of the cone of delta at height Q. Okay. So remember, we would originally we would append for a lattice polytope a 1. In this case, I'm taking the generators to be Q so that I have an actual integral ray generator. Okay. And so I'm just here defining some notation. And so here's a little lemma. If I fix a triangulation T with denominator Q of a rational polytope, and I let the simplices be in the triangulation, or I'm taking all the simplices in the triangulation, the H-star polynomial is in fact just the sum of the box polynomials coming from each subsimplex in my simplices from the triangulation. Okay. And so here is the result. I won't proof sketch it for you. But now this is the first decomposition, which says it is a sum of box polynomials times H polynomials. Note that the box polynomials all have coefficients 1, right, by definition. So these are always positive. And it turns out that H polynomials are also always positive. And so if you're multiplying positive times positive, you get positive. And so you can see a roundabout way to proving Stanley's monotonicity, or we get Stanley's Stanley's non-negativity result from this decomposition. Okay. So it's now 10:15. So I'm going to just skip over these things. And I will say that we use that Beckett-McMullen decomposition, that rational Beckett-McMullen decomposition, to give a different proof to Stanley's monotonicity result. And I'll say that Stanley's original monotonicity result proof was very algebraic. And I want to believe that our result is more discrete geometrical, even though we have some underlying Cohen-Macaulay stuff popping up in the background. And so I'll, again, time's running out, and I just want to show you the last decomposition. Actually, I'll just skip all the way to the end and tell you one of the other results we got about from getting a decomposition. So a result separately from Stanley and Hebe is, so one, what is an open problem in Erhart theory? An open problem in Erhart theory is, can you classify Erhart polynomials? And you can also say, can you classify somehow Erhart quasi polynomials? And what does that mean? Well, we would have to actually either fix, a period or a dimension, right? But that's a very difficult question because it's already open even for Erhart polynomials, meaning for the lattice polytope case. And so what is one next best thing? And so towards that direction, we give some inequalities that are satisfied by the Hdr polynomials. And so I should say that this is now generalizes the results of Stanley and Hebe, where they proved these inequalities that are satisfied by the Hdr polynomial for lattice polytopes. And here we have it for rational polytopes. And I think with that is all I'll say today.
Thank you very much, Andres, and let's everyone thank Andres for a wonderful talk.
Thank you. Sorry, that was kind of fast, but I did not realize 15 minutes was.
It's tough. It's tough to fit something in 15 minutes. I think we have time for a couple of short questions. So, Galen, do you want to unmute yourself and ask your question?
Yeah, I had a clarification question just when we were defining the fundamental parallelepiped, which is, should I be thinking of this half openness as somehow keeping track of independent vectors that tell me about that fundamental parallelepiped?
Can you tell me more? What do you like? What do you mean?
So when we defined we defined some open parallelepiped, and then we defined a half open version.
Right.
And the half open version has like some extra. You're introducing some stuff.
Yeah. So okay. So maybe I'm cutting you off, but I'll say this, and maybe this is a roundabout also way to answering your question, is that and Jody can correct me if I'm wrong, in the cone, you can tile the cone of a polytope by the fundamental parallelepiped. And so in a sense, you're keeping track of all the lattice points and you're never overcounting in that cone. Yeah. So I don't know if that partially answered your question, Galen. Yeah.
I think we have time for one more question. I have a small question about H-star polynomials. So you were saying that you didn't assume that the expression was simplified, right? Or in lowest terms.
Yeah.
Is there an interpretation when you can cancel one of these factors, 1 minus c to the q? Does that give you information?
I'm not aware of that, but that would be a good question. Jody, has that popped up anywhere in your stuff? No, I don't. I've never thought about reducing it and what does that entail, geometrically or something, but that might be a good question. Yeah, and I think there was another question if we still have time. I can't see.
Yes, there's a question from Galen.
Or no, but I think somebody else had a hand up. I think.
Oh, sorry, I think I missed it. If the person wants to unmute themselves, they can ask.
Yeah, I was just curious about, you said it was palindromic and your result.
Oh, and I did not answer it. And it's because I did not answer it because I did not present my second decomposition. But I will say that in that second decomposition, I split the Hdr polynomial into two polynomials that end up having non-negative coefficients. And from there, from that that decomposition is where I'm able to get these inequalities that are satisfied by the Hdr polynomial. And so we call this an A-B decomposition. And so A is a polynomial and B is a polynomial. And so for that particular example, it turns out that the B polynomial in my decomposition that I did not show you turns out to be 0. And whenever it's 0, we should be getting a symmetric non-negative polynomial. And that's exactly this A polynomial in my A-B decomposition. Yeah, thank you for reminding me. And again, 15 minutes is too short to show all the stuff that I wanted. But yeah, thanks to you all for your attention.
Let's thank Andres again for a wonderful talk.